slides. Do you have any questions? Did you find any problems trying to solve the homework set? So please let me know now. Did you manage to do all the exercises?
Anyone can say something?
I've had a problem finding the representation of the rotational group elements.
Aha. What kind of problem?
I didn't really know how to do it, so I managed to write the vector representation, so the matrices in the vector representation, but I don't really know what the rotational representation is and how vectors rotate, and so.
Yeah, that's something which is sometimes is a bit confusing the first time. What did you do to obtain the matrices for the vector representation? How did you do it? For instance, let me see. I need the slide. Let me just go back to this corresponding slide.
For example, for the mirror on the x-plane or something.
Yeah, that's easy to do. But for instance, how did you find the mirror? I mean, how did you find this? Sigma D2, let me see what this was. Sigma D2 is this. This is sigma D2. This is 60 degrees. So in this case, we are supposed to obtain for the vector this thing here. Did you manage to obtain this matrix, for instance? I mean, you don't need it if you just want to compute characters. But sometimes when you are working with group theory, you do have to be able to compute matrices like this one. Did you manage to do it?
So for me, I know how to do this.
You don't know how to do this, okay? So
I know.
Oh, you know how to do this. How do you do it?
I look at the axis, how the axis transform, and I look where the x-axis lands after transformation.
Okay, yeah, that's one way. I mean, the first thing, I'm going to insist on this because this is a source of endless confusion, at least at the beginning. You have to make a big difference between components and vectors. Let's call them E1, E2, E1, EX, EY, Z. Okay, this should be the basis vectors. So this is X, Y, Z, EX, EY, Z. And now, any vector, in this case, any position, the vector can be written like this. And this usually we just write like this. Okay. So now you have to have very clear how to act on these things with the group elements. The first thing that you should know is that when one speaks of the matrices of the representation, one assumes that the action is this, that this vector is prime. Is just this matrix B2 times X, Y, Z. So that's the first thing, that these matrices are supposed to act on column vectors. Okay. That's very important. It doesn't act on EX, EY, EZ, and things like that. No, it acts on column vectors given by their coordinates. So that's one thing. Now, the second thing is how you construct these metrics. Well, even at this point, there is some ambiguity. I haven't mentioned that yet, but assume that you have this coordinate system and you want to act with a C3 plus. This is 120 degrees rotation, okay? So now, depending on which book you are considering, people use what they call the active or passive interpretation of the group operations. The difference is very simple. In the active representation, and that's the one I will always use because that's the one most people use, and I think it's more intuitive. Under a symmetry, one rotates the objects, not the coordinate system. The coordinate system does not change. But for instance, if I have a vector here, vector v, then I rotate the vector v prime. If you want r, okay, the vector r. Okay, so this is the active representation. In the active representations, the coordinate system does not change. I do rotate the objects. I say objects because you can consider vectors, but you can also consider polarization tensors. You can consider all kinds of things, as we'll see partly today. Okay, that's the one we always use. In the passive representation, what one does is vectors don't rotate, but one rotates the system. The reference system vector stays the same. So it's very important not to confuse these two things because one is the opposite of the other. If you think a little, if I rotate the vector like this vector goes to this. That's one thing. If I rotate the system like this, it's like rotating the vector by the opposite angle. So we will always stick on this. Okay. So we never change the coordinate system. This doesn't mean that we don't change the coordinates. That's another source of endless confusion. Sometimes people don't distinguish between coordinate system and coordinates. These are completely different things. The coordinate system is just the axis that you use. I use this axis, this is the x-axis, and this is the y-axis. This is the coordinate system. The coordinates is if I have a vector r, this is x for this vector, and this is y for this vector. So these are entirely different things. In the active interpretation, I don't change the axis, I don't change the coordinate system, but I rotate the vector. Obviously, if I rotate the vector, the coordinates of the vector change. Okay? But I don't rotate the coordinate system. Well, now, and this is almost the end of this observation, what happens if here I write this 1, 0, 0? Let's see what happens. So my initial coordinates are these. So I take this vector. Well, the first thing that you realize is that this vector, according to this, is just EX. Okay. So now X prime, Y prime, Z prime are going to be just the coordinates of the rotated vector. I take this EX. If I rotate it, it becomes E prime X. I have rotated this unit vector. Okay. So now let's apply this matrix to this unit vector and see what we get. That's what it is. Well, I multiply. So the first one gives me -1/2. The second one gives me -2, and then 0. So this is just Ex prime. Is the effect of the unit vector by a 120 degrees rotation. And now you see, this is what? This is exactly the first column of the matrix. As you can see, it's obvious that it has to be like this. If you see what the mechanics of the matrix multiplication is. If now I take the second unit vector, then immediately you find that the transform of the second unit vector is just the second column. Okay? And this is, of course, the transform of the third unit vector. So it's very important, and this is the recipe that I always use to construct a matrix. I never use this formula with cosine, sine, because they are only good for very particular axes. If you are in a general situation, what is always relatively easy is to see what the transform of the unit vectors are. So what's the recipe? Very simple. You want to construct for any representation T of G. In this case, it's the vector representation, but it can be any other representation of any dimension. So basically, I have a basis of vectors, and the basis is always like this. A basis. Well, then I look at this vector, this object, see how this is transformed, and then I have something like this. I see that under G, this vector goes into something. So this something I place here. Is the first column. So the first column is E1 prime, the E1 transformed by the operation. The second column is the E2 transform, etc. So that's the recipe that I always use, and I always recommend, because in general it's extremely hard to try to use general formulas with a rotation group and with planes and things like that. But this is always relatively easy to do. So let's apply this to this element, sigma D2, see how this works. Please stop me if anything is not clear. So, sigma D2 is the axis, clearly. Y, and sigma D2 is this plane. Right? Yes, this is sigma D2. This is 30 degrees. And now let's try to construct the matrix, or the vector representation. So for the first column, I just have to take this vector, Ex, which has components 1, 0, 0, and see what the new components of the vector are. Well, this is 120. If I reflect this on this plane, this is going to be 120. Okay? Or if you want, if this is 60, this is 60. It's exactly the same thing. Okay? So basically, what this means, I mean, that's the only thing. You need some kind of mental gymnastics to do this. Usually you reduce very easily. So I have this, and this is E prime X. E prime X, the components are quite obvious. The X component is -1/2. The Y component is -√3/2, and the Z component is 0. So here I place -1/2, -√2, and 0. Let's see if I got it right. Because, yeah, okay. and you see the mechanics. You can do exactly the same thing. Is that clear? How I got this? So I'm not using any particular formula. I'm just looking at the picture and writing what I see. Okay. Now the second one. This is fine. Well, in this case, I have to see what happens when I rotate this one. Well, this is a plane, this is 30 degrees, so this has to be the same 30 degrees. So this is 30 degrees. And then the components, this is EY prime, the components are obviously minus square root of 3/2, 1/2, and 0. Yes. And then obviously, if I take now the vector like this one is unchanged because it's parallel to the plane. So this is just this. Okay. So that's one way to get it. Excuse me, the person who asked, Johannes, how did you do it? Did you use this method or did you use a different method?
I did it that way.
Okay, yeah, very good. So I think it's the most efficient. But I mean, usually most people are not aware of this way of doing things, so that's why I explained it. Now, question with pseudo vectors. Pseudo vectors belong to the rotational representation. That's the way of speaking in group theory. When I say that an object belongs to a representation, is short for this object transforms according to this representation. So pseudo vectors transform according to the rotational representation. Pseudo vectors or axial vectors. Okay. So now, when it comes to proper operations, and proper operations are just rotations, pure rotations, no inversion, no reflections, things like that, they transform identically. So in this case, for the elements E, plus, minus, they are exactly the same thing, okay? Now, what happens for the other operations, improper operations? Well, in general, there is just a relative minus sign. I'll explain in a minute why, okay? There is a minus sign. So for instance, if we have obtained for sigma d1, first I give you the recipe, which is what's really important, and then we'll see why this one. Then this I just change, I just use an overall minus sign, and that's it. It's really simple to construct one from the other. Well, the reason this works is just the following. By definition, I mean, proper operations are always rotations. See, by n anchor. These are proper operations. Then I have the inversion, spatial inversion, which is improper. And then you remember that when I combine I with an axis, I take this, which was related, I don't remember the exact formula, but I think it was something like this, with a rotor reflection. But this doesn't really matter. What really matters is that all other improper operations are always constructed as the inversion times some rotation. Okay? Now, in the vector representation, the inversion is like this. It's the unit matrix. In the rotational representation, by definition of axial vector, That's exactly what an axial vector is. There are physical reasons for it, but I remind you. Okay, this is just reverse. An ordinary vector, like the electric field, under inversion, it becomes minus itself. That's the definition of, that's true for vectors, okay? However, if I take something that the angular momentum, since this is a wedge product of two vectors, this goes to minus r minus k, so it goes to itself. And that's the general, that's the general rule for pseudovectors. Pseudovectors, V of r, sorry, I didn't do it wrong. R of I is just the identity. So the rule is V of the identity is 1 for vectors, and for pseudovectors, plus 1. Now, since any improper operation is always the product of a rotation times the inversion, this means that for proper operations, I just have a relative minus sign. Is that clear? So immediately, I have to flip this. And that's the general rule. You take the vector representation and the matrices for the improper operations, and this means rotor reflections, inversion, and reflections, relative minus sign. It's very interesting, the implications of this, because they are rather counterintuitive. Consider, for instance, this one. This is sigma, is the plane, sigma d1. These are our axis, x and y. And this is the matrix for a pseudovector. So this means that this reverses the x and z components. And it doesn't change the y component. And that's exactly the opposite of what happens for a vector. If I have a vector like this, a vector v, if I reflect it on this plane, it becomes this. However, if I have a pseudo vector like this, let's say a magnetic field, and I reflect it on the plane, it becomes this. Sorry, it becomes this. So for a magnetic field, when I reflect a magnetic field on a mirror which is parallel to the magnetic field, it changes sign. When it's perpendicular to the magnetic field, it doesn't change sign. And that's very easy to understand physically. Assume that I have a mirror like this, and here I have a current. And this current is creating this magnetic field. Now, if I see the current in the mirror, the current goes like this. So it's creating a magnetic field like this. So parallel components of pseudovectors change sign. Perpendicular components, if I do the same thing, you see that this doesn't change. Don't change. So this is a bit counterintuitive, but that's the way things are. Okay. So I hope this answers your question. So it's very simple. Just for for improper operations, relative minus sign, and that's it. Okay. If you look at the general formulas that I gave you last time, you will see that that's also the relation between the two. Okay. Any more questions regarding the exercises or any other thing? Because
I have a question. Can you hear me?
Yes.
It's more a curiosity in the sense that in the exercise there were we were given the methane molecule and the boron trifluoride. So in both of them, one of the atoms is inequivalent in a sense to the other. So there is carbon in the center, and in the other there is boron. So just to think, I was thinking, in case, stoichiometrically it is not meaningful, but if the central molecule was also equivalent to the others, the point group, from what I understand, would not change. The mechanical representation would not change. So in a sense, I would expect the vibrational spectra to have the same degeneracy. But intuitively, the fact that the central molecule is inequivalent makes also sense that the spectrum should be somehow different. I mean, these are molecules, so you cannot have at the center of replace a carbon with hydrogen. But say that this was a macroscopic mechanical object, or like some photonic nanoparticle you want to study the vibration of. The fact that the central atom is equivalent or inequivalent, how would affect the spectra? It would affect just in the sense of quantitatively, or would leave some degeneracies?
I'm not sure I really understand your question.
Yes.
I mean, you are saying that in this, for the boron fluoride, this atom is different. Now, okay, so the question is, what happens if this were identical to the others?
Yeah, I mean, chemically doesn't make sense, but if it was a particle or an object.
Yeah. No, okay, no, that's a very good question. I mean, the point is that this doesn't change at all the symmetry of the molecule, as you noticed. If this is a planar, then if this is planar, this or this, they have identical symmetry group. So in principle, the qualitative features, and so far we have only studied qualitative features. I mean, group theory is also useful to help studying quantitative properties. But for qualitative features, I mean, the degeneracies and this, I would say that they are identical. Another thing is if you consider non-planar molecules, because if you consider non-planar molecules, and that's what we were doing, something like this. Now, if this atom is different, I mean, I just lift it, okay? I lift it and then I have C3D, okay? But if I lift it the right amount and the atom is identical, suddenly I get a tetrahedron, and suddenly the symmetry increases. So from the viewpoint of group theory, these things are pretty much undistinguishable for the planar molecule, okay?
And for the methane was the same. For methane is the same situation. For a methane molecule, CH4 is the same.
Yes.
Yeah.
Okay, in that case, that was different because in the case of methane, I have this, and now if I change this, I break a lot of symmetries of the tetrahedron. Okay, a tetrahedron, for instance, if you take, I mean, let me draw a tetrahedron like this. This is a tetrahedron. Around each vertex, you have this 120 rotational symmetry. If this is different from this, I mean, these rotations, you have this in your tables. Let me tell you on which.
Yeah, but actually here the carbon was at the center of the tetrahedron.
Yes.
Right?
But of course, but the carbon didn't play any role.
Yeah, that's my question.
No,
the
but
carbon
it was
doesn't
this,
play.
where you have H or D.
Okay.
That's closer to your example, okay? I mean,
Yes.
Yeah, that's closer. In that case, that was very important, but that's because that was exactly at the right height.
Yeah.
If this was not at the right height, it wouldn't make much difference, okay? Of course, then when you look at the quantitative results, there might be big differences.
Okay, I see.
But the qualitative aspects, I mean, the things that in principle gives you directly group theory don't change at all, because as long as you don't change the symmetry group, there is no change.
Okay. Thank you very much.
Okay. More questions? Okay, if there are no more questions, let's go to today's presentation. So I'm going to share. Okay, I'm sharing screen, and now Okay. So far, the only operations that we have performed with representations have been addition and subtraction. When we decompose the mechanical representation, we write this as a sum of irreps, okay? And then when we want to obtain, for instance, the vibrational representation, I just subtract the rotational and the vector. Today, we're going to learn to take products of representations, which is very important. This is very important for two reasons. One reason is that now you have a recipe to analyze the spectrum of a molecule. You know how to do all the computations. And at the end, you can find exactly how many different frequencies you have, what the degeneracies are of each of these frequencies. Okay, but you don't know why this works. I never proved that the degeneracy of any rep is, that the dimension of any rep has to be equal to the, exactly equal to the degeneracy, or that the multiplicity has to be equal to the number of frequencies associated to that rep. Okay, so today we are going to prove this in a practical example. If you want formal proof, you must go to the books. We'll do an example. If you understand the example, you really understand any proof that you can see on any book. Okay, and then we will also consider properties, physical properties of molecules, later on of crystals. Now, the thing is that physical properties, they are usually described, as you probably all know, by tensors, not by vectors. For instance, the first one we are going to consider is the polarizability of a molecule, and that's described by a symmetric rank 2 tensor. Okay, so we have to learn how tensors transform. When we do this, we will also learn why all this stuff about molecules and the vibrational spectrum of molecules works. Because in fact, in that case, the tensor is the dynamical matrix. Okay, so let's consider first molecular polarizability. This is going to be very important for next lecture when we consider Raman effect. Raman effect is related very much to the polarizability tensor. Now, well, this is just a linear description of the induced dipole moment, electric dipole moment of a molecule under an applied electric field. In general, for a non-isotropic molecule, these two things are not parallel, and this is a tensor. Okay, so in components, that's how we do it. I always assume that is a sum over repeated indices. Okay, so unless I say otherwise, whenever you see a repeated index, that implies a sum, because it's a lot easier to write equations like this. Okay. Now, you know that this is a tensor, and you know that tensors transform like the products of coordinates. Okay. In fact, that's the definition of tensor. What is a tensor? A tensor is something that transforms like the products of coordinates. What is a vector? Vector is something that transforms like the coordinates. Okay, the components of a vector transform like the coordinates of a point. So this means that since the vector has two indices, I and j, I have to use the vector representation on each of the indices. Okay, this would be the transformation of xk, xl, because this transforms by the product of coordinates. Okay, this transforms like xk, times xl. So I just transform each of them. Now, this you can write in matrix form like this. You have to take the transpose, because you see this ik, kl, but then I need lj. So I take the transpose. And then now you know that under rotations, under reflections, all these things, these transformations are always unitary or orthogonal, if you want. They always preserve the norm. And you know that for an orthogonal matrix, the transpose is equal to the inverse. For a unitary matrix, the Hermitian conjugate is equal to the inverse. So I can write it like this. And you see that this is nothing but a similarity transformation. Okay, that you know since you were in kindergarten. Okay, so it's relatively easy to go from vectors to tensors. I just have to use the vector representation, but twice, in front and after. Now, assume that I want to study the polarizability of the deuterated methane, or maybe of methane, okay? Now, the polarizability describes a property of the molecule in equilibrium, and then it must be invariant under all the symmetries of the molecule. I mean, if I have a molecule and I say that something is symmetry, but when I make this transformation, the polarizability changes, I'm obviously lying. That's not a symmetry. The molecule looks different. Otherwise, it would have exactly the same polarizability. So this means that the transform polarizability, which is this, has to be equal to the polarizability. But now, if you multiply this thing on the right by V of G, you find that V alpha is equal to alpha V. So this means that alpha commutes with all the matrices in the vector representation. So invariance of a rank 2 tensor is related to this commutation. In fact, all of this is totally elementary. I'm sure all of you have seen this before. And in fact, that's a way to compute, probably you have used in a solid state introductory course and things like this, to find the form of the different tensors. You can find how many independent components you have for the polarizability tensor of a crystal with some symmetry. And all you do is this. You construct this representation. You write the most general rank 2 symmetric tensor, and you impose these constraints. And from this, you find the independent components. Okay, that's very simple, but it takes quite a while. And if you try to do the same thing, let's say for the elastic tensor, which is a 6 by 6 matrix, you may run into trouble quite easily, but still it can be done. So what I'm going to teach you is how to do this automatically if you know some group theory. And from the point of view of group theory, this is almost trivial to do. So that's what you are going to learn today. So instead of using the standard method of computing all these commutators and from this finding the relations between the different components of alpha, we'll use group theory. It's much, much more efficient, as you will see. Now, when you want to do this with a tensor like alpha, it's always easier if you involve the tensor into a scalar. For instance, if you multiply alpha ij times ej, you obtain the polarizability. So this means that the product of the polarizability times, the polarization or the electric dipole moment times the electric field, the product of polarization and electric field is the energy, proportional. I mean, it's 1/2 and things like that, but I don't care about these things, okay? So this means that this quantity, this is just the tensor contracted with the electric field, this must be invariant. Why? Because if the molecule doesn't change under a rotation, their energy cannot change, okay? So from this, we have two facts. First, the energy of a molecule subject to an electrostatic field is quadratic in the electric field, okay? So it is given by a quadratic form, or in other words, a symmetric second rank tensor. On the other hand, the energy must be a linear combination of quadratic invariance in the electric field. Why? Because the energy must be invariant. Okay, because it's a property, it's a scalar, and if the molecule is invariant under a symmetry, this cannot change, otherwise it will be invariant. Okay. So this means that the most general formula for the energy has to be necessarily a linear combination of quadratic invariance in the electric field. Okay. And now let's use loop theory. We are talking about the electric field. The electric field transforms according to the vector representation. And for the deuterated methane molecule, that's the one I'm considering, this is invariant under the group C3V. And we know, and you have done this in the exercises, that that's the decomposition of the vector representation. There is A1, which is the trivial or identity representation for the EZ component, and this is the electric field. Okay. And now the very, very important observation. Sorry. Here I have three involved representations: the V, A1, and E. All these representations are unitary. Why? Well, first, vectors, you know that when I rotate vectors, the scalar product doesn't change. That's the definition of a unitary representation. Okay, so this is physically unitary. These are irreps, these are abstract objects, but still, there is a theorem. If you are reading some book, you have already encountered it for sure. There is a theorem that tells that for a finite group, and this is a finite group, it only has 6 elements, you can always, if you are given any representation, you can always find an equivalent representation which is unitary. And unitary representations are very convenient to work with. So when you use tables of irreps, the irreps that you find are always unitary, just because this is very convenient. Okay, so any representation of a finite group, you can always find an equivalent representation which is unitary. So in general, we tend to work always with unitary representations because they have a number of nice properties. Okay. So this means that the norms at scalar groups are invariant under the symmetry group. For instance, for this representation, the norm of the electric field is EX squared plus EY squared plus EZ squared. This has to be an invariant, okay? This cannot change. And you know that this is true. The norm of the electric field doesn't change when I rotate it. This is obvious. But also, and this is something that you wouldn't know, this representation A1 is unitary. So the norm here, which is EZ squared, is invariant necessarily. Why? Because this is unitary. This representation is unitary. So the norm of this vector EX, EY, which is EX squared plus EY squared, must also be invariant. Okay. So immediately I have two invariants. So this is the mechanics. I have V with an irrep and another irrep. Then automatically, if I take the norm in A1 and I write this thing this way, you will see later on why I write it like this. I take the norm here, this is EZ squared. If I take the norm here, this is EX squared plus EY squared. So automatically I have obtained with no effort, no commutation, no anything, two linearly independent quadratic invariants. At the end of the lecture, we will see that there is only one invariant for each irreducible representation. If I have an irreducible representation, this is obviously an invariant, and this is the only one. Well, in this case, it's obvious because this is the only invariant, this is the only quadratic thing that I can construct from EZ. However, from here, I could construct other quadratic things. I could construct also EX times EY. Well, there is the theorem that I'll prove at the end of today's lecture, if I have time, that tells you that from any irreducible representation like this, from just one irreducible representation, the only invariant is the norm, EX squared plus EY squared. So this means that we have obtained all the invariants. Well, you may say we have another invariant because the norm of this is also invariant, EX squared plus EY squared plus EZ squared, but this is a linear combination of these two, okay? So if you want to find all the linearly independent quadratic invariants, you just look at the irreps and the corresponding norms and just the invariants. Okay, so this means that the energy, which is even like this, necessarily is a combination of these two things. So it only depends on two constants. In matrix form, this is this. So we have obtained, with very, very little effort, the most general form of the polarizability for any molecule with symmetry C3V. See, we have not really used the structure of the molecule. We have only used the symmetry group of the molecule. So this is valid for any molecule or any system that has the symmetry C3V. I tell you, the standard method, I mean, for somebody who doesn't know group theory, you'll have written A, B, C, D, E, here symmetry, and then impose that this commutes with the group elements. You'll find a lot of linear equations, and at the end, you end up with this. But if you know group theory, all you do is this. You write this, this, and this. Here is all the computation if you know group theory, okay? So group theory tells you how to obtain invariant tensors. Yes, quadratic invariant tensors. In the future, we'll learn how to construct more complicated tensors. So any questions so far? Well, the reason I write this is because, as we'll see, this thing belongs to this product representation. Why? Well, it's very simple. This transforms according to A1, this transforms according to A1. I'm taking, this is really the tensor product of this space with itself. There's only one element. So we'll see that the definition of product of representations is just the representation for the tensor space, for the tensor product space. We'll see that at the end, okay? So far, just concentrate on the fact that we are computing norms and that norms are invariant because these things are unitary. Okay, so now we are going to extend this.
Sorry, I do have a question to that.
Yes.
How exactly do you arrive at that E of EX y times E of EX EY is equivalent to EX squared plus EY squared?
So, sorry, say it again.
How exactly do you arrive at the equation that E of EX EY times E of EX EY is equivalent to EX squared plus EY squared?
No, it's not. No, that's not really. No. Sorry, I didn't explain it well. No, the idea is the following. This is really, I'm taking the tensor product of this space. So the tensor product, the tensors in this space transform like the products of coordinates. I have three products of coordinates: EX squared, EY squared, and EX EY. Okay, so really in this tensor product, I will have, it will be a three-dimensional space with three quadratic forms: EX squared, EY squared, and EX EY. However, only this linear combination, only this one is invariant, okay? So there are two different things. One thing is that this thing has more elements than this one. It has also EX squared minus EY squared and EX EY as independent quadratic forms, but they are not invariant. So these are two different things, okay? This is in this representation, but this is not the whole representation. It's just one element, the one that happens to be invariant. Does it clarify a bit your question? I mean, I'll be, at the end, I will be more formal, but that's what I mean by this, that I'm studying products of coordinates. Whenever I study product of coordinates, I study tensors. Whenever I study tensors, I'm taking the product of the representations, okay? This last statement I haven't justified at all, okay?
Can I ask something that's a bit
Yeah.
related to this? So when I used to do this, I used to look at the character tables. If you look at the character table that you find in any table, in any like book or something, you have like what quadratic functions are like into what representation, like transform what as a specific representation. So in this case, if you look at the C3V table, for A1, you have exactly X squared plus Y squared and Z squared. So I thought that the general rule is that whatever kind of quadratic or cubic, depending on what I think it's what's relevant for the specific tensor, transforms as the fully symmetric representation would be the like this linear combination you need to make. It does make sense. Is that
Yeah, no, that's right. No. Yeah, I have the impression that you know more than I mean,
yeah,
you,
so I
you
just
already know
want
some group theory.
well.
No, okay. I'm deliberately being imprecise, because if I'm too precise, people get lost. No, strictly speaking, if I'm considering quadratic forms, in other words, if I take here electric field and here electric field, I'm taking the symmetric product of these two representations, which is not exactly the same as the tensor product. But we'll see this, and on next lecture, I'll make all these differences. If I give too many details, I'm always afraid that people will get lost. But you are right. I mean, I have to make a clear distinction. I mean, I can take the tensor product, I can take a symmetrized tensor product, anti-symmetrized. When I take cubic things, I can take all kinds of different symmetries. I mean, that probably you know that they are described by Jan Tableau and things like that. But okay, I don't want to go into this so early, okay? I don't know if this answers, well, I know this doesn't, I mean, you are right, but I don't want to go into it, okay?
Okay, thank you.
Okay. Okay, so now we'll try to do exactly the same thing with the molecule. This is a bit more complicated because the molecule, instead of vectors, the relevant objects here are the displacements of all the atoms. I'm going to do it for the deuterated methane molecule. So I have 5 atoms. So I'm going to be working in a 15-dimensional space. So things are a little bit more complicated in that sense. If you try to do that, what I'm going to do today using the conventional method of writing the most general metrics, you have to write the most general 15 by 15 metrics. Then you have to construct all the 15 by 15 matrices of the mechanical representation and compute all the commutators and find an awful lot of linear relations. Well, you can spend probably several evenings doing this, and most likely you will get it wrong because it's almost impossible to do it wrong. Of course, if you use Mathematica, then the thing, you can do it quite fast, but still it's not a very efficient method, okay? So this is going to be a bit more complicated because the space is a bit more complicated. And also I have to remind you of some peculiarities of the dynamics of a molecule, okay? So that's what I'm going to do next. What I'm going to do next is physics. It's not really group theory. I'm sure you have seen this before, but I have to remind you of it because otherwise you won't know what I'm doing. Okay, so why doesn't it work? Okay. Now, okay, before I do that, we can do this also for the methane molecule. Methane has TD. For methane, you have computed this in one of the exercises. The vector representation is already an irreducible representation. Ex, Ey, Ez is a 3-dimensional representation. If you have done the exercises, that was on exercise 1.5, I think, yes, it's TD. And the vector representation is T2. And the only quadratic invariant is this. In this case, there is only one quadratic invariant. So this means that the polarizability is isotropic, okay? Again, if you do this by hand, you have to do a lot of commutators. Here is obvious, okay? This will be very important when we consider the Raman effect, the rotational Raman effect next time, okay? Well, so now let's go to molecular vibrations. I do it in general first. A molecule has 8 atoms. So the configuration of the deformed molecule is described by this vector. It's just I give the displacements of each atom, okay? So the positions of the atoms are the equilibrium positions plus the displacements, okay? These are the equilibrium positions of the atoms. These are the displacements. Now, the kinetic energy would be just taking the derivative of this. If I take the time derivative of this gives me 0 because these are equilibrium positions, these are constant. So I just get this, okay? This I can write in matrix form by considering this U as a 15 component vector. This is the transpose. And then the mass matrix is just a diagonal matrix with elements M1, M1, M1 for the first atom, then M2, 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 etc. Okay, so in matrix form, this is just given by the mass matrix. Okay, the kinetic energy is just this quadratic form in the velocities and the mass matrix. Okay, now I consider the potential energy. The potential energy in the harmonic approximation, all I do is I take the potential, I expand up to second order in the equilibrium and in the displacements, and these elements, well, this is the form for the kinetic and for the potential energy. I mean, when you study phonons, you do this, for instance, for crystals. For molecules, it's exactly the same thing. You expand the potential energy up to second order, and then you find a quadratic form, which is given by this. So this means that the Lagrangian for the molecule vibrations is just given by this in matrix form. Now you can use Lagrange equations, just vary U, and you find immediately the equations of motion. And the equations of motions have just this form. M times the second derivative of this 15-dimensional vector plus U times this 15-dimensional vector must be equal to 0. Now, you know how to solve this. You use these ansatz. U of t, you assume that all the atoms are vibrating in unison. They are vibrating with the same frequency. You use, of course, complex notation instead of cosine, which is inconvenient. You know, I mean, that the real displacements are the real part of this, okay? And this is just a 15-dimensional vector, okay? And this is called a normal mode. A normal mode means that all the atoms are vibrating in unison. It means exactly with the same frequency, exactly in phase, but with different amplitudes. And the amplitudes are described by the normal mode, okay? So if you substitute this thing into this matrix equation, you immediately find this thing here. And basically, you have to solve for this. So basically, in principle, it's just a diagonalization problem. But it's not a completely trivial or completely standard diagonalization problem. It's not the standard eigenvalue problems, because a standard eigenvalue problem would be UN equal omega square n. Here I have this matrix in the middle. So U acting on n is not proportional to n. So n is not an eigenvector in the standard sense, okay? But this is very well known how to avoid this problem. Basically, we make a change of variables. I take a new displacement vector, which I find by multiplying the original displacement vector by the square root of the mass matrix. How do you take the square root of a matrix? Well, you diagonalize it and you take the square root of the eigen values. Okay, so since this is already diagonal, it's trivial. That's the reason that when you learn about phonons and things like that, you always find this square root of the masses in everywhere. This is just to convert this thing into a standard eigenvalue problem. Then, if you use this transformation here, and also this transformation with the mass matrix, you end up with this Lagrangian. The kinetic energy becomes just the unit matrix, basically because we have incorporated the masses into the definition of the displacements. And then this matrix, the new potential matrix, is related with the old one by this. But this is just a technicality. With this technicality, then I do have an eigenvalue problem. And in this case, if I diagonalize this transform potential matrix, I immediately obtain the eigenfrequencies or the proper frequencies. And these vectors are the normal modes, but of course, with this square root of m's everywhere. Okay, but the idea is that we are going to concentrate on this thing. This object will try to see what is the most general form of this object allowed by the symmetries of the problem. When I solve this, since this is a 3A by 3A matrix, in our case 15 by 15, I will get 15 frequencies, okay, with the corresponding normal modes. But of course, you know that 6 of these frequencies are 0 because they correspond to uniform translations or global rotations, okay? This, you know that when you diagonalize a Hermitian matrix, the eigenvectors are orthonormal. So basically, this is given by this. Okay, the scalar product is just taking this. So this gives you this. Now, if you revert to the original coordinates, this means that the normal modes, and the modes that we use here in our ansatz, they are orthogonal, but they are orthogonal not with respect to the trivial scalar product, but with respect to this mass matrix. In other words, it's like computing a norm or a distance with a non-trivial matrix, a non-trivial metric. The mass matrix is the metric in the space of normal modes. All of this probably you have seen in the course in mechanics. If you haven't seen, well, I think that probably what I'm giving you is more than enough to understand what we are going to do. Now, what are pure vibrations? We are really interested in pure vibrations. Remember that the mechanical representation was decomposed into the vector, which tells you how uniform translations transform, the rotation, that tells you how rotations, axial vectors transform, plus the vibrational, that tells you how pure vibrations transform. So this means that the mechanical representation, which in our case acts on a 15-dimensional space, it means that on this space I can consider 3 subspaces. The space of pure translations. These are very easy. All the U's are equal. The U's for all the atoms are the same. I give the same translation T to all the atoms. This U lives in this space, the space of global translations. Then here are global rotations. I forgot to mention that the equilibrium positions are always considered with respect to the center of mass of the molecule for dynamical reasons, okay? Otherwise, you remember that angular momentum, you have to be careful. When you have a system, everything was a lot easier if you compute angular momentum with respect to the center of mass. Well, that's, in this case, I also consider the equilibrium positions measured with respect to the center of mass of the molecule. And then this represents a rotation around the center of mass, okay? Because if I rotate the molecule around the center of mass, then this is a pure rotation. If I rotate the molecule around a different point, this is equivalent to a rotation plus a translation. So if I really want to separate cleanly rotations from translations, I have to use the center of mass, okay? And then the space of vibrations is defined by these constraints. So this space is very simple. This space is very simple. Sorry, very simple. The space of pure vibration is not simple at all. It's a space which is given by constraints. So it's a really complicated space. You see, the constraints are these. This means that a pure vibration doesn't move the center of mass, okay? Remember, this gives you the center of mass. Under a pure vibration, the center of mass doesn't change because this gives you the position of the center of mass. Well, you have to divide by the total mass, but this means that a pure vibration does not displace the center of mass. Also, there is not associated angular momentum. I will have to divide this by time or time the derivative, but this doesn't really change the thing. This means that a pure vibration does not involve any global rotation of the molecule. Or dynamically, when the film is vibrating, there is no angular momentum. If I take the time derivative, you see this is the angular momentum. So this space is really complicated. So this means that if you want to study pure vibrations by brute force, the problem is kind of horrendous. I mean, you have to construct this space, which is defined by a lot of constraints. Then you have to construct the 9x9 representation for these vibrations. It's really horrendous. So you really need group theory to do this. Group theory just jumps over all of this. But anyway, that's what we are really doing. We are considering these three subspaces, and we are going to concentrate on this one. Okay. Now, I'll give you as an exercise next time. You can check that these three spaces are orthogonal with respect to the mass metrics. In other words, if I take two displacements of the molecule, my scalar product, if I define with respect to the matrix product, then you can check, and you'll do that in an exercise, is that these three subspaces are orthogonal. That's very important from a technical viewpoint. It's not important for what we are going to do. But if you are reading formal group theory, you have learned that when I decompose every representation into irreducible representations, and I want anything to be unitary, which is usually the case, the corresponding invariant subspaces have to be or are automatically orthogonal with respect to each other. So that's the reason I'm introducing this rather technical point here. Okay. I have to take some water for my throat, so let's take a break of 2 or 3 minutes. I'll be back. Okay, so Well, okay, so we are going to consider first the methane molecule. You have done that in one exercise, in exercise 1.6. And in that case, and I mean, from the slides, you also know that this was the decomposition for the vibrational representation. It was A1 plus C plus 2T2, okay? This is one-dimensional, this is two-dimensional, and this is a three-dimensional representation. As I told you, and if you have looked at the tables, A and B are reserved for one-dimensional irreps, E for two-dimensional irreps, and T for three-dimensional irreps, okay? And now let's assume that we are using symmetry-adapted coordinates. What do I mean by this? Remember, for C3V, the vector representation was reducible into A1 plus E, but the structure of the matrices, the block diagonal structure of the matrices was obvious only if you choose an appropriate coordinate system, which was the XYZ. If I use a different coordinate system, I lose completely the block structure. So here we are going to assume that in this 9-dimensional space, because the space of vibration is just 9-dimensional, we are choosing coordinates such that the block structure is obvious, okay? You don't know yet how to obtain these coordinates. This is non-trivial, but there are methods in group theory to obtain them. There's the method of projectors, basically, okay? That we'll see, I think it's a couple of lectures from now. Okay? So we assume that we are using symmetry-adapted coordinates and in such a way that all the block structure is obvious. Now, the normal modes and frequencies are obtained by diagonalizing the potential matrix. I mean, this transform potential matrix, okay? So now we want to know what is the most general structure of this potential matrix in this coordinate system allowed by the symmetries. So this is very similar, now that you know all these technicalities about the vibrations of molecules, to the problem of the polarizability. In the case of the polarizability, we choose symmetry adapted coordinates x, y, z, ex, ey, ez, and on these coordinates it took a very simple form. Now we are similarly choosing symmetry adapter coordinates, and on these coordinates we want to see what is the most general structure of the vibrational matrix allowed by symmetry. Okay, is that completely clear? Please stop me at this point if this is not completely clear, because that's crucial for the rest. Okay, so now it's again the same thing. This is an operator. This is a RAM2 tensor. So it transforms by a similarity transformation with respect to, in general, the mechanical representation. Okay. In our case, I mean, this is a typo. Well, if I consider the general matrix, it will be by the mechanical representation. If I consider just the 9 by 9 matrix, it would be the vibrational representation. Okay. And again, these constraints can be solved more easily by considering the invariance of the potential energy. Out of this matrix, I can construct a scalar, which is the potential energy. This potential energy has to be invariant under all the symmetries of the molecule. Therefore, this has to be a linear combination of invariants constructed in the symmetric coordinates. Okay. In fact, I mean, this next time if I have, I'll explain that on the blackboard. In fact, when you go to these symmetry adapted coordinates, you have, I mean, you have a potential matrix which is 15 by 15, But in this symmetry adapted coordinates, this reduces to something which is 9 by 9, which is the purely vibrational part. And then all the other things are zeros because they just correspond to translations and rotations. Okay, so we concentrate just on these coordinates which are purely vibrational and where the matrix is non-trivial. And now we are going to use exactly the same method as for the polarizability. First, I write with like this, okay, with the symmetry adapted coordinates for the different irreps. There are three different irreps. These two are the same, but they appear twice. This means that there is one subspace given by these coordinates that transforms according to T2, and another subspace given by these different coordinates that transform also like T2. Okay. So now I proceed exactly as we did for the polarizability. A1, the only thing that I can construct is the norm, which is Q1 squared. So this is one invariant. Here I have E. Since this is a unitary transformation, I know that the norm is an invariant, and that's the only thing that I can construct. It's just the norm. Now here, this is the first representation which has multiplicity non-equal to 1. I mean, this appears only once, this appears only once, but this T2 appears twice. There are two subspaces. So now here I can construct more invariants. First, since this is unitary, the norm is an invariant. This is this norm. Since this is unitary, the norm is an invariant. But now I can construct also the scalar product because this vector and this vector transform identically because it's the same representation. And since the representation is unitary, not only norms are conserved, also scalar products. So I can construct this scalar product. So this is the novelty with respect to the very simple case of the polarizability. When you have complicated representations, bigger representations, it's rather common to have multiplicities different from zero. I mean, you can have different subspaces that transform identically. They transform under the same irrep. So if I take the scalar product, this of course is also an invariant. Okay. So this means that if it's true that only scalar products and norms are invariants, these are all the invariants that I can use to construct the potential energy for vibrations. Okay. Remember that translations and rotations don't have any potential energy. If I translate the molecule, the bonds of the molecule are unchanged, so this doesn't generate any potential energy. If I rotate it globally, the distances between atoms don't change, therefore this doesn't generate any potential energy. So this is really the total potential energy has to be a linear combination of these 5 invariants. Okay. So this shows that the most general potential energy for the methane molecule depends only on 5 free parameters. Let's construct it. It's very simple. I take my 5 invariants and I write the most general combination of the 5 invariants. So I get this with coefficients A, B, C, D, and 2E. Why do I write these two? Because I want to write this in matrix form. Remember that when you write in matrix form, you are going to have Q4, Q7 plus Q7, Q4. And each of them with a coefficient E, so that gives you 2E, Q4, Q7, okay? Just remember, when you have a quadratic form, extra diagonal elements carry an extra factor of 2 due to the fact that this represents Q4 times Q7 plus Q7 times Q4, okay? So if I write this in matrix form, I get this form for the potential energy, which is kind of ugly. This is easy to understand. Q1 is only involved in this term. So this is A, Q2 and Q3. This is Q2 squared, Q3 squared. I mean, all the diagonals are here. And now this involves Q4 times Q7, this is this E, and Q7 times Q4, this is this E. Okay, so I'm just translating this quadratic form into a matrix. It's a matrix representation for a quadratic form. But this is kind of ugly. I mean, there are no blocks. There is something which is diagonal, and then this, I have this thing off diagonal, but where are the blocks? Okay, it's not very promising so far. But now we use a trick that you have used a lot in your course on quantum physics. Probably in your first course on quantum physics, or the second semester, when you study perturbation theory, and you study, for instance, the Zeeman effect, Stark effect, things like this, you realize that sometimes things simplify very much if you just reorder the wave functions. Here we are going to use the same trick. Here, this is written in this order: Q1, Q2, Q3, Q4, etc. But this is not a very smart thing to do. We're going to reorder it in this way. I'm going to take Q1, I'm going to take Q2, Q3, and now instead of taking Q4, Q5, Q6, and Q7, Q8, Q9, I'm going to take the first of this one and the first of this one. So Q4, Q7. The second and the second, Q8, Q5, Q8. Now the third and the third, Q6, Q9. I mean, this is just a change of basis. I just order my coordinates in a different way. And now, if you look at the previous, at this quadratic form, you will see that with this new organization of the coordinates, this has a much, much nicer form. It's exactly the same quadratic form, but with this new ordering, which is very precise, it's just when you have a repeat representation, always choose first the first two vectors, then the second, etc. And this has a very nice block diagonal form. Okay. This represents this quadratic form. There is nothing new. Okay, it's just writing these things. So see what a nice structure this metric has, and this is enforced by the symmetries. I have a one-dimensional representation. So the corresponding coefficient is here. This is two-dimensional. Now the corresponding coefficient, which was b q2 squared plus q3 squared, appears repeat here. And now this is the nicest thing. That's the reason I'm using the methane molecule rather than the deuterated methane, because here I have a multiplicity which is equal to 2, because this appears twice, but I have a degeneracy which is equal to 3. So you see, if I have multiplicity 2, I have 2 by 2 blocks. So the multiplicity tells you the dimension of the blocks. This multiplicity is 1, so these blocks are 1 times 1. But this is multiplicity 2, so this gives me, by construction, blocks which are 2 by 2. Okay. What is the manifestation of the degeneracy? The manifestation of the degeneracy is that this block appears repeat 3 times. And this is Wigner's theorems, exactly. Wigner's theorem. It tells you that when you consider something which is an invariant, like the energy, the corresponding matrix, and it's quadratic, I mean, it's a second order thing, must have this structure. You must have, for each representation, a matrix which is equal to the multiplicity of the representation. These two have multiplicity 1, so they correspond 1 by 1 matrices. And the dimensions are reflected into a repetition of the block. This has dimension 2, so this appears twice. This has dimension 3, this appears 3 times. And now this is a lot easier to diagonalize. This is already diagonal. So this means that these things are already frequencies. Remember that the eigenvalues of this matrix were the square frequencies squared. So this means that the frequency associated to A1 is just this element. Now, the frequency associated to E is just this element, but disappears twice. So it's the same frequency, but with degeneracy 2, because it appears twice in the diagonal. I have 2 equal eigenvalues. And now I have to diagonalize this one. So when I diagonalize this very simple 2 by 2 matrix, I get the 2 extra frequencies. Since T2 appears twice, multiplicity is 2, I have 2 different frequencies. In general, these 2 frequencies are different unless there is some accident. But these frequencies appear 3 times. I mean, when I diagonalize this, I'll have here omega 1 square, omega 2 square, omega 1 square, omega 2 square, omega 1 square, omega 2 square. So I'll get something completely diagonal, but the frequencies will have some repetitions, okay? So what is the general rule? Just what I was telling you. When you decompose the vibrational representation, and you have, among this sum, you have a irreducible representation tau I with multiplicity mi. In the decomposition of VIV, I mean in the matrix VIV, there are the identical n by n matrices in the diagonal of the potential. Okay? So the multiplicity gives you the dimension of the block matrix, and the dimension gives the repetition, how many times this matrix appears. Okay? So that's the rule that we have shown experimentally, quote unquote, by doing a case, but it's obvious that to formalize this is completely trivial. It's just you need a lot of indices and a lot of things, and it's easy to get very confused, but obviously this is always going to work. Okay. Okay, so let me just comment on this. This is the formal part of today's lecture. First, the product representation. Rank 2 tensors, I'm speaking of tensors, Euclidean tensors or vectors, Tij live in the 9-dimensional space, which is this tensor space, and transform like the product of coordinates. So in general, tensors Ij, not necessarily symmetric, this is general, general tensors, 2 by 2, 3 by 3, I mean, sorry, rank 2 tensors, Euclidean tensors, live on this space, like the polarizability. The polarizability is special in that it's symmetrical and it lives in a smaller space. Okay, we'll see that next time. But let's forget about the symmetrical case in general. Rank 2 tensors belong to the product representations. By definition, the way these 9 products of coordinates transform is the V² representation. This is just a definition. Okay, so you see that taking the product of a representation is associated to taking a tensor product of linear spaces. This is also called the Kronecker product. Okay, in some books, that's the way you'll find it. In general, for 2 representations, T1 and T2, acting on spaces of dimensions D1 and D2, the tensors in the tensor product belong to the product representation by definition. And we'll show next time that the character of the tensor representation is very simple. It's just the product of the characters of the factors. Okay, so I'm going to stop here. You can look at this at home. This is just a proof that if you have 2 irreducible representations and you take the tensor product of the 2, the only invariant is the scalar product if the 2 representations are equivalent, and there are no invariants otherwise. So this shows, please look at this at home if you don't understand something. First thing, next lecture, I'll go through this. Okay, if you understand it, then I will explain it. But this is just the proof, the formal proof that this way of constructing invariants by taking scalar products and norms gives you all the invariants, the quadratic invariants. There are no other invariants. Okay, be careful. This is true for real representations. Real representations are representations where the matrices can be made real. Okay, but we'll say more about this next lectures. Okay, so we'll stop here. That's the end of today's lecture.
Thank you, Juan Luis. Has anyone any question? Okay, if not, we meet again next Wednesday. It's always the same link. I tried to send an email before, but if I don't because I forget, just join to the same link. If there is any week without a lecture, we will say it in advance. And slides can be downloaded from the user link too. I'll let you know when Juan Luis has uploaded them.
Okay.
So if that's all, then see you all next week.
See you.
Bye.